Okay, so before we can get into how to calculate bond energy, I want to go over a little reminder dealing with bonds. And you're going to actually find that during the course of the notes today, that there is some old material that you need to remember how to do in order to do these calculations as well. So, a reminder of what covalent bonds are. A covalent bond is a sharing of electrons. And what's key here is when they share electrons enough times in the right ratio, however you want to refer to it, they can reach stability. A very large theme in chemistry is the idea of stability. Stability is a good thing. Unstable things, a lot of energy involved. We do a little miniature unit at the end of the year on nuclear chemistry. Radioactivity, again, fusion versus fission, so both the energy source for power plants and then the bomb type. Instability, a lot of energy involved with that. Well, stability, there's energy involved with that as well. So we want to go over a little bit of this before we get into the mathematics behind it. To remind you of how a bond is created, I have a picture in the upper right-hand corner of a diatomic hydrogen, an HH bond. How does that occur? Orbitals are overlapping between two atoms. And in doing so, the positive nucleus of one atom is attracted not only to its electron, but to another electron. And in doing so, you see in that picture in the upper right-hand corner, each hydrogen atom now has two electrons around it. One of its own, one from the neighbor. That makes it stable. It has a full outer shell. Remember, it's that 1s2 full inner shell, just like helium. It's a noble gas configuration. When things are stable, it's almost like breathing a sigh of relief. Hydrogen atom on its own, not stable. It only has one electron. It creates a bond with anything. It has two electrons around it. It's now stable. It can release energy. Because when you're stable, you don't have to have a lot of energy to hold you together. Think about if any of you have ever watched little kids. Little kids that sit there and do nothing are pretty easy, and it doesn't require you energy to keep them entertained. I mean, that's babysitters who pop in a movie and just, hey, go ahead. Little kids that are running around crazy nonstop, that requires more energy. When you are unstable, it's not easy. When you're stable, it is easy. And why we go over this is, very beginning of the year, we discussed the conservation of mass law. Even some of you in the stoichiometry today used stoichiometry when you wrote a balanced equation and you included oxygen as a product because you knew I can't just get rid of oxygen. But early in the year, we asked you a question before a lab. And that question was, you weigh less when you wake up in the morning than when you went to bed the night before. And the number one answer that students would say of why do you weigh less is because you're burning calories. Just like if you exercise, if you run around a whole bunch, you might lose weight, you might lose mass. Too often, people relate energy and mass, which is wrong. After all, calorie is a unit of energy. So when you say you're burning calories, that says you think you using energy means you lose mass. Indirectly, sure. Directly, no. What we're going over today is two things. One, the idea of where does energy come from in a chemical reaction. Because our world works based upon energy. And we need energy when we flick on a light switch to get electricity to go in here. We need energy to power our lives. How many did you drive to school today in an automobile? That requires gasoline to power that combustion reaction. because that's a combustion reaction that's occurring to create energy to make your vehicle get from point A to point B. Again, me talking right now, I am using up energy. Remember cellular respiration in biology class. You know, they'll talk about ATP versus ADP, but in here we can actually go over where that energy comes from. And that's my last statement on this slide. The energy required involved with breaking bonds and forming new ones is what bond energy is about. And in chemical reactions, because this is the reaction unit, we need to go over that idea of where does the energy come from and where does it go to. It requires energy to break a bond because when atoms bond, they are stable. If you are going to break them apart, you are getting them further away from that octet, that full outer shell. You're getting them further away from stability. Year after year, assistant principals send out an email before school dances asking to, hey, who wants to chaperone for prom or homecoming, whatever it is. I delete that as fast as possible because my Saturday night does not need to be, you know, watching high schoolers getting a little too close to each other. My Saturday night spent grading your labs. But if two high schoolers were getting a little too close to each other on the dance floor, it would require energy from a chaperone to separate them. It requires energy to separate two atoms that are bonded together. I mean, quite frankly, some people dance like they are bonded together. Right, Connor? It's a little too much. Now, think about it. If those two individuals that are dancing together are right up on each other, I mean, it's going to take a lot of energy to break them apart. However, if they've got like a 6-inch gap between them, it's not going to take as much energy to break them apart. If they are dancing with their butts out because they barely want to touch each other, it's going to be easy to break them apart. The further away two atoms are from one another, the easier it is to break them apart. There's not as much attraction between their positive nucleus and the negative electrons. But the closer they are together, the harder it is to break them apart, just like teenagers on a dance floor. So that's what this second bullet point's referring to. The shorter the bond length, and we talked about bond length first semester. You guys might not remember it very well, but it's a topic that we went over. The shorter the length between the two atoms, the more energy is needed to break them apart. Just like two individuals on a dance floor. I mean, we could base this off of violence and say two people fighting each other as well. But we're all about love and chemistry, not about violence. My sub-bullet point here. Another thing that we went over first semester that might have slipped through your mind after all the stuff we've been going over this year. A single bond is longer than a double bond. Do you remember the idea of a double bond? Like O double bonded to O when you draw your Lewis dot. Don't worry, you're going to remember Lewis dot in about 10 minutes here. Yes. Triple bonds are even shorter than that. So the closer they are together, harder it is to break them apart. And we have numerical values for this. On the flip side, if breaking two atoms apart requires energy, the forming of bonds, when two things come together, they are now more stable. They would release energy. You have those high schoolers that are nervous of, oh, should I ask her to dance, should I not? And they're just using all this energy pacing around and around and around. And finally, when they meet that special someone and they do dance together, they are now more stable. They are no longer using all that energy thinking about, oh, should I, shouldn't I? It's just, oh, you can breathe a sigh of relief. Well, when atoms are unstable because they're at the octet, that's not an energy efficient way to exist. But when they bond with something, they are now more stable. And in the world of thermodynamics, of explaining how energy transfers occur, more stable means energy can be released. My first bullet point and my third bullet point are the basis of the math that we do. We understand in order to make a chemical reaction occur, reactants to products, we have to break apart the reactants. I believe I even used the analogy of it's like playing the jumble, where you make new things. Now you guys have seen patterns at this point this year. Single displacement, what's the pattern for the reaction? So it's not just a random new products, you guys know how to predict the products. Double displacement, you know how to predict the products. Combustion, you always know the products. Synthesis, there's only one product at the end, so we know how to put that together. So you've seen the pattern. But what I'm telling you is our next step in chemical reactions is to be able to identify how much energy does it take to break apart the reactants. Because if we're going to make something new with it, we got to break it apart first. It's like my kids playing Legos all the time. If they want to build something new, they have to break something apart to make something new. Well, it takes energy to break things apart. And then when they put new things back together, now we don't have to worry so much about having this bad guy anymore. My son's all about everything has to have bad guys in it. Any movie that's on TV, who's the bad guy in this? Eddie, I don't know. Some movies don't have bad guys. It's just a love story. So why are we watching it? I know why. Last thing to mention on this page. And now, after this, we can get into the calculation that you have to know. There is a page in your textbook that will give you a table that shows bond length and energy. Now, I will give you this on assessments otherwise, but I just wanted to have you know that there are pages in the book that go over this topic as well. So after today, if we're still a little confused, you could reference your textbook because it does talk about this. It does give examples of where we get the data from. But otherwise, my goal on these first two slides was to give you some background. Instead of just immediately jumping into the math, we learned this because our world runs on energy. And we feel it's important that chemistry students understand where energy comes from. Because at the beginning of the year, I bet 2/3 of you, minimum, felt that mass gets destroyed and turned into energy, and that's how things work. And for the vast majority of the energy that's created on our planet, that is not the case. I didn't say all, because we do have to talk about nuclear reactions in the last unit, which is one of the exceptions to the rule. Okay, so our goal then is to solve a problem like this. So I'm going to go over this with you step by step. How much energy is needed or created depends during the decomposition of hydrogen peroxide. What I'm going to do is show you the steps that you need to do to solve this on this slide. Then on the next slide, I'm going to actually work the problem. So maybe you don't have to write everything down that I'm about to show you. Okay? So if we have the question up here, I think that's good enough to start with. What you would have to do, again, I don't think you have to write this down, is I would give you a table, or I just give you the values of bond energy. Different types of bonds require different amounts of energy. So for example, a hydrogen-oxygen bond has 459 kilojoules per mole. Kilojoule is a unit of energy, just like calorie is a unit of energy. A joule is a unit of energy. Quite frankly, I had my in-laws go to Africa a while ago, and they brought me back chocolate. And then when you look on the back side at the energy content, it gives you grams first off for everything there. But then the energy content on here, instead of giving calories, it gives you joules for the energy instead, because that's the international unit for energy, is joules. OO single bond, 142 kilojoules per mole. OO double bond, 499. Notice how a double bond has more energy than a single bond. You could think of it as, well, I have to break two bonds, but remember, it's also a shorter bond. Shorter bonds require more energy. Okay, so we'd have to give you this information to solve this problem. What you would eventually do, again, you don't have to write this down because we're actually going to solve this instead. Just like stoichiometry, though, you cannot solve bond energy without writing a balanced equation. So you have to do that to start off with. Then, yes, we get to draw a Lewis dot now again. Boy, I've been missing that. Yeah, that's right, Dorn. Dixon, Noah's, get ready for it. Lewis dot drawings again. Reason why we have to do that is we have to know how many of these different types of bonds exist in the reactants and the products. Once we do that, maybe this last step 3 is the one thing that you want to write down before we solve it. To solve for bond energy, the energy change within a reaction. This little goofy A thing here is called, come on, how many are far enough in math to know this symbol? Is it sigma? Yeah. It means the sum. You need to take the sum of all the bond energy of the reactants, subtract the bond energy of the products. Some textbooks will refer to it as input versus output. So how much energy do you put in? How much energy do you get back? Because remember, you have to put energy in order to make it break apart stable bonds. Last slide. Oh, I'm sorry. This last bullet point is actually something that we should jot down. There are two terms on this last slide, exothermic and endothermic. We did do thermal chemistry at the beginning of this unit. I'm sorry, beginning of this semester. Remember things like you put the hot iron in the water in the styrofoam cup? Ice melting, phase change with those heating cooling curves for water. Not only are we going to require that you do the calculation that I'm about to show you, but we should be able to identify a chemical reaction as either an endothermic reaction or an exothermic reaction. An endothermic reaction means more heat is put in than given off. So there's a net input of energy. Every chemical reaction is going to have reactants require energy to break apart and products give off energy when they form. But if there's more input than output, it's endothermic. Exothermic means heat is given off. That means that the products are more stable than the reactants because it took more energy. It takes less energy to break apart the reactants than is given off afterwards. Now notice on my last bullet point here, when we solve our step number 3, if our answer is a negative value, that means it's exothermic. If it's a positive value, that means it's endothermic. So those are two terms that we did use at the beginning of the semester when we did thermal chemistry. I just want you to be aware of them again in terms of bond energy. For this, then we could go to the last slide that actually goes over the math. We ready? Okay. Here's our balanced equation. I actually did this reaction for you when I gave you notes the last time on the 5 reaction types. It was that elephant's toothpaste one where all of a sudden the soap bubbles gained oxygen and they bubbled up and they went all over the place. So there's the chemical reaction. What I'm going to do for a second then is I'm going to switch over to Smart Notebook and draw out the Lewis dot for these things. In order to do bond energy, you need a balanced equation. However, you also need the Lewis dot for everything in that balanced equation. So I'll rewrite that reaction right here. Okay. Let's take Lewis dot a little slow to remind you. Hydrogen has one valence electron. How many does oxygen have? Which column is it in? 6. So remember, the Lewis dot for oxygen would be 1, 2, 3, 4, 5, 6. Oops. Sparkboard does not calibrate well. There's 2 oxygens in this, so I'm going to do that again. And a second hydrogen. If I were to do the Lewis dot, remember the idea of lone electrons want to pair up. In other words, hydrogen and oxygen would create a bond right here. Hydrogen and oxygen create a bond right here. Hydrogen, when it creates one bond, is already stable. The oxygen, however, has 1, 2, 3, 4, 5, 6, 7 electrons around it. It would bond with the other oxygen. Now again, partly because my smartboard isn't calibrated, so my dots are off, but also with all these circles, I'm going to neaten this up a little bit. The Lewis dot for hydrogen peroxide is that. Again, sorry for the lines being a little off for some reason. Wherever I'm writing, it's not allowing me to do. So here's the Lewis dot for hydrogen peroxide. The Lewis dot for water. Oh, I hope we remember this one. I mean, we had to draw dissolving and actually during notes I referenced the oxygen Lewis dot. Oxygen is double bonded to another oxygen. Here's what I can tell you about the Lewis dot. We're not going to give you the most difficult Lewis dots in the world. We're going to try to keep it simple for you. As simple as we can with still making you show this type of work. All right. Here's the next thing I'm going to do for organization's sake. I want to figure out all of my reactants. Because then I'm going to subtract all of my products. Okay, you ready? You see I have an HO bond right here? Right? I have an HO bond. How many HO bonds are in one hydrogen peroxide? 2, right? 1 here and 1 there. However, how many hydrogen peroxides do I have in this reaction? 2. So how many total hydrogen-oxygen bonds need to be broken here? 4. So right now what I'm doing is I'm kind of organizing what's happening here. I have 4 HO bonds in the reactants that have to be broken. Not only do I have HO bonds, I have an OO bond. Uh-oh. There's 1 OO bond in hydrogen peroxide. However, there are 2 hydrogen peroxides in the formula. So I'm going to say that I have 2 OO bonds. This is all of the reactant bonds that have to be broken. I need to subtract from that all of the product bonds that are formed. My first product is water. It has 2 HO bonds, but there are 2 waters in the formula. So I have a total of 4 HO bonds. My second product is oxygen. We need to be careful with this. there is one OO double bond. There's a difference between a single bond and a double bond, and you can't just multiply by 2 for a single bond. So there's one OO double bond. There's a coefficient of 1 in front of that. So there's one OO bond. I'm going to go back to the PowerPoint note here then. That's what we just figured out. Here's how we do the calculation. Previous slide, I told you that an HO bond is 459 kilojoules per mole. So I just substituted that in for my HO bond. That's what you just wrote down. An OO single bond is 142. So I just substituted that in. This is all of my reactants. Here's my 459 from the HO. Here's my 499 from the OO double bond. The mistakes that students make on bond energy problems, part of it comes down to organization. So I like to figure out how many of each type of bond do I have, then plug it in. And actually, when you see my final answer here of negative 215 kilojoules per mole, which means it's exothermic, by the way, because it gave off heat, I typically actually first solve for my reactants, then minus, and then my products. Because algebra with this and how you type it into your calculator is one of the major errors that come up when doing a bond energy problem. So when we work on bond energy, it's important to organize. How do we grade bond energy? We give you 1 point for writing the balanced equation, because you have to have it. We give you 1 point for doing the Lewis dot typically, because if you don't have the Lewis dot, you don't know how many of each type of bonds you have. And then we give you probably 2 points for your total amount of work. Reactants minus products. Notice the negative answer indicating that this is an exothermic reaction, which, by the way, when I did that elephant's toothpaste demonstration over here and all the foam came up, after a while I bet a lot of you saw steam as well, because there's enough energy given off that some of that water was evaporating too. Energy comes from bonds. It does not come from matter being destroyed. We can numerically solve for that amount of energy, and that's the goal with what we are doing today.